Hey folks, welcome back to class. Today I want to take you on a journey to learn about what I call hypertriangles and hypertriangular numbers, to see some surprising facts and mysteries about how many dimensions each number is hypertriangular in, and which numbers are the most multidimensionally metatriangular. First, let me explain what I mean by a hypertriangle. Let's say I had a zero-dimensional point, and I wanted to add another point and connect them. Well, I end up having a line segment. Now, let's say I wanted to add another point that wasn't on the same line that this line segment lies on, and then connect that, and maybe even fill in between everything that had been connected. I would end up with a triangle. Now, could I take that further? Well, if I wanted to add another point that wasn't on the plane the triangle was on, like another point up here, and connect that and everything in between, I would end up with a tetrahedron, also known as a triangular pyramid. In many ways, a tetrahedron is like a three-dimensional triangle. And although that may be the limit in the third dimension, if I could take another point in some fourth dimension somewhere that was outside of the whole 3D space this lived in, and connect that to this in a similar way to this extension we've been doing, I would end up with what's basically a four-dimensional triangle. These generalizations of triangles are often called the simplex shapes, but I think they also deserve to have the nickname hypertriangles. Now, these hypertriangles are shapes, so let me explain what I mean by hypertriangular numbers. Now, there are several triangular patterns that could lead us to these numbers, and perhaps the simplest is to imagine a sequence of piles that each just contain one item per pile. But then we're going to stack these and look at what happened when we had stacked one of them, then two of them, then three of them, and that would give us the whole numbers. And then if we similarly stack the whole numbers, looking at the first, then the first plus second, then the first plus second plus third, we end up with what are known as the triangular numbers. And we can stack those on top of each other as well in the third dimension, creating what are known as tetrahedral numbers. The sum of the first triangular number, then the sum of the first two triangular numbers, and so on. Now that may seem like the limit, but it's more the limit of what humans can easily visualize. Mathematically, we can take tetrahedrons or tetrahedral numbers and stack them on top of each other without any weird overlaps if we had another dimension to do it in. So mathematically, we can figure out which lists of numbers would emerge as the higher dimensional versions of triangular to tetrahedral to beyond, making new sequences essentially where each term in them was the sum of all of the terms up to that point in the previous sequence, and we would end up with higher dimensional generalizations of triangular numbers, which often are called the simplicial polytope numbers or the n-simplex numbers. But when we take cubes and put those in higher dimensions, they get all sorts of fun nicknames. Like people would call a 4D version of this a tesseract or a hypercube. So I personally like to refer to the simplex shapes as the hypertriangular shapes, and I like to refer to the numbers we would get by mathematically stacking triangular numbers again and again as hypertriangular numbers, and I like to call a number's metatriangularity the amount of different dimensions it is hypertriangular in. And when I call these the hypertriangular numbers, it's not just because we would notice them if we counted dots and then balls in higher dimensions. These numbers also catalog another fundamental trait about triangles in higher dimensions. Let's say you noticed that a triangle has three vertices, three edges, and one face. And then you noticed that a tetrahedron has four vertices and four faces but has 6 edges. Why those numbers exactly? Well, if you looked at what would happen mathematically with how many of different traits higher dimensions of hypertriangles would have, we would see an alternate layout of the same numbers we saw in those sequences. So these numbers are hypertriangular in multiple ways. The most common way of presenting these hypertriangular numbers, as I like to call them, is within this classic array of numbers called Pascal's triangle. And due to all of the cool ways you can create and view this triangle, many people miss out on the fact that it describes different dimensions of triangles in multiple different ways. Not only can we see the diagonals of this as representative of the triangular numbers, as well as their 0-dimensional and 1-dimensional versions, and then their 3-dimensional versions, the tetrahedral numbers, and beyond, or we could view that with the diagonals coming the other direction because of the symmetry here. But also, if we look at the straight horizontal rows, those can be seen as describing how many of different aspects like vertices and edges and faces triangular shapes have in different dimensions. Plus, this array of numbers ends up having a triangular shape itself. And as I've shown in a previous episode, if we look at this with modular arithmetic, such as taking the even numbers and odd numbers in it and coloring them different colors, we end up seeing fractal-like shapes that are triangles within triangles within triangles. So this really is a triangle of hypertriangles in many ways, but that is lost within many of the other ways you can view this triangle. Many people simply see this as an array you could create if you begin with a 1, imagine it with zeros going infinitely on either side of it that we will then ignore, and then we create new lines where each term is the sum of the two above it. But that does end up turning out to be equivalent to the way that we were stacking things to create triangular numbers and then tetrahedral numbers and so on. Now, we can also view this triangle of numbers as what are called binomial coefficients. Binomial coefficients are the coefficients you get if you were to expand something with 2 variables, or sometimes you'll see this presented as x plus 1 to different powers, but it does technically work with x plus whatever y we're trying to figure it out for. Here we'll see coefficients of 1, 1, 1, 2, 1, 1, 3, 3, 1. Next, we would see coefficients of 1, 4, 6, 4, 1, because that's another way of creating or viewing this triangle. The fact that these binomial expansions create the rows of Pascal's triangle relates to the fact that if you take the powers of 11 up to a certain point, you'll notice that 11 squared has the digits 1, 2, 1, 11 cubed is 1, 3, 3, 1, 11 to the 4th power is 1, 4, 6, 4, 1, and then after that point the digits overlap in a way that makes it stop working. And in any basic base, the digit string 1, 1 raised to different powers will look like rows of Pascal's triangle up to a certain point. And the binomial coefficients have another really cool connection. They also turn out to describe the amount of ways you could select items out of some set of items. Let's say you had these 4 types of fruit and you were allowed to choose some amount of them, and you wanted to know how many different ways you could select some amount of these if the order you selected them didn't matter. For example, there is technically one way to select none of them, the way of selecting nothing, and there are 4 ways to select one of them, and you'll notice there are 6 ways to select 2 of them, and there are 4 ways of picking 3 of them, or 1 way of picking 4 of them, and all of those numbers we encountered, 1, 4, 6, 4, 1, are a row of this triangle here. Each of these rows, if we start with the top being called row 0, describes if I had some amount of items, which is the row number, and then starting with picking 0 of them and then picking 1 of them, all the way up to picking the full amount of the row number of them, it shows how many ways, if order didn't matter, I would have of selecting that many of them. And that can help this symmetry here make more sense, because it makes sense that there would be the same way of selecting 3 out of 4 items as of selecting 1 out of 4 items, because we could view one of those cases, the ones we did select, as a mirror of the ones we didn't select in the other of those cases. Now, selecting m items out of a set of n is known as n choose m, and is often written like this. So here is what Pascal's triangle looks like when we write it under that interpretation. And although this doesn't show us the exact number that lands on each spot in the way we're used to seeing them in base 10, we would have to calculate it, which we can do with a simple formula involving factorials. Looking at Pascal's triangle this way can let us incorporate some notable identities to get clues about traits like how meta-triangular a given number is. For example, the number 1 will appear an infinite amount of times here, because for any row n choose 0 always equals 1. Additionally, every whole number will appear here at least once due to what I call trivial hypertriangularity, where n choose 1 always equals n. Additionally, these appearances of 1 and whatever n that is will also have mirrors if there's enough room, due to what I call the symmetrical rule, where for any n and any m, n choose m is exactly equal to n choose n minus m. This will cause any number that appears in a row here to appear again in that row in a symmetrical way, unless the number appeared in the direct center of a row. Those numbers that appear in the direct center, like 2, 6, and 20, are known as central binomial coefficients, and here they're notable because they are the only numbers that could appear an odd number of times in total. And each number apart from 1 will have some finite amount of times that it appears, because a number n cannot appear beyond row n. Apart from the number 1, which will be on the ends of any row n, anything else within a row n will be numbers n or larger. Normally, any whole number will appear at least twice due to its trivial triangularity and the reflection of that, although the number 2 is unique in only appearing once, whereas any other whole number will have a reflection to its trivial triangularity that is different. Another notable example is the number 3. 3 is large enough that its trivial hypertriangularity does have a separate reflection we'll see here, but it's small enough that the fact that it is a regular 2D triangular number doesn't have room to contribute anything extra. That overlaps with its trivial hypertriangularity at this size. To see this visually, 3 doesn't appear in this inner triangle, which contains all the numbers larger than 1 that appear more than twice total, such as the next 2D triangular number 6. 6 is large enough that its 2D triangular nature does show up separately, but it's small enough that that 2D triangularity doesn't have a separate reflection. It lands right in the middle of a row. So 6 appears exactly 3 times, whereas 2D triangular numbers larger than that are guaranteed to appear at least 4 times. Their trivial case, their 2D triangular case, and a reflection of each of those. And that brings us to our next 2D triangular number, 10. 10 may seem extra notable here because it's 2D triangular and 3D tetrahedral, related to the fact that the sum of the first 4 whole numbers equals the sum of the sums of the first 3 whole numbers. However, its tetrahedral nature can be seen as the automatic symmetrical mirror that we're guaranteed to get from it being a 2D triangular number larger than 6. Any 2D triangular number larger than 6 will have another dimension that mirrors that in triangularity, and with the number 10, it just happens to land at a neighboring dimension, making its patterns easier to visualize, but making it only appear 4 times. Unlike the other numbers larger than it that are both 2D triangular and 3D tetrahedral, such as the next number of that type, the good old number that used to be called the long hundred, 120. You can also notice that I mentioned here no known number appears exactly 5 times. And it's actually true that there is no known number that appears an odd amount of times more than 3 times. All central binomial coefficients that are 6 or larger will appear 3 or more times, but none are known that appear more than 3 times. All known numbers that appear more than 3 times have an even number of appearances that come in a symmetrical way. So after ones that appear 4 times, we get to the numbers that appear 6 times. Now this is the point where metatriangularity becomes much rarer. It's not very hard to find a number that appears 4 times in Pascal's triangle, and thus is hypertriangular in 4 dimensions. In fact, any typical 2D triangular number larger than 6 will have that trait. However, the numbers that appear more than 4 times are very rare. Now, as far as numbers that are both tetrahedral and triangular, meaning they're hypertriangular specifically in dimensions 2 and 3, it has been proven that these are the only triangular tetrahedral numbers. Now, 1 does appear an infinite amount of times in Pascal's triangle, and as I noted, 10 has its triangular and tetrahedral nature be mirrors of each other, as opposed to each getting their own separate mirror. But the ones larger than 10 on this list do appear 6 times. Now, this list is finite, but to appear in Pascal's triangle 6 times, you really only need to be hypertriangular in 2 different dimensions that don't overlap in any way with the trivial case or the symmetrical reflection of anything. And these were the numbers that fit that for specifically dimensions 2 and 3. But if we allow numbers that have another pair of dimensions that they are non-trivially and non-overlappingly hypertriangular in, we will also meet these notable numbers. And the only known numbers that are hypertriangular in more than 4 dimensions are the ones I have on screen here and one other very special family. You see, if you analyzed the first trillion or so whole numbers to see which ones appeared in Pascal's triangle more than 4 times, you would only find these numbers and the number 3003. And even if you looked up to a quadrillion or a quintillion, you wouldn't find any more, But it turns out that 3003 is a member of an infinite family of numbers that all appear 6 or more times, and that family of numbers just grows so quickly that the next term you'd meet is far bigger than 1 quintillion. Despite the size of these numbers, though, they actually have a really simple and cool formula, which is surprisingly related to the number sequence known as the Fibonacci sequence, which starts with a 0 and then a 1, and then each further term is the sum of the 2 terms before it. The Fibonacci numbers we would get from this process also have another more well-known connection with Pascal's triangle, where if you take the numbers in each row of Pascal's triangle and add them up, the rows of Pascal's triangle add up to the powers of 2. Then, if you take the numbers in each of these slightly diagonal lines that have an angle somewhere between those horizontal rows and the infinitely long main diagonals, well, these slightly diagonal lines, all the numbers on them add up to exactly the Fibonacci numbers. And some of you may have already known that connection, but I bet almost none of you know about this lesser known connection between the Fibonacci numbers and the realm of metatriangularity. So let me show you a simplified, alternate but equivalent version of the formula that was discovered by the mathematician David Singmaster. What we're gonna do is take the Fibonacci sequence and the index of each term, beginning with calling the 0 at the start the 0th term, and we're going to pick a number k, and we're going to create two numbers n and m such that n equals the Fibonacci number with index twice k times the Fibonacci number 1 after that, and m equals the Fibonacci number with index twice k times the Fibonacci number 1 before that, and we will be guaranteed that n choose m minus 1 is exactly equal to n minus 1 choose m. And each of these does have a reflection. In general, the reflections of this can be simplified to n choose n minus m plus 1 and n minus 1 choose n minus m minus 1, in addition to a trivial triangularity and the reflection of that. So any number in this family will appear at least 6 times. For example, the number 3003 shows up in this family because if I pick k being equal to 2, then I have the 4th Fibonacci number times the 5th for that n value, and the 4th Fibonacci number times the 3rd for that m value. And here, when I end up doing 15 choose 6 minus 1, or 15 minus 1 choose 6, I end up with 3003 for both of those. So 3003 came out of this formula when we picked k equals 2, and if I had picked k equals 3, I would have gotten the next member of the family instead, and here's the one for k equals 4, and the one for k equals 5, and as you can see, they get big pretty quickly. But this family of numbers does change a lot about what we know about the landscape of metatriangularity. Without this family, less than a dozen numbers would be known that are hypertriangular in more than 4 dimensions. But with this family, we know that there are definitely an infinite amount of numbers like that. But that isn't quite the end, because the most surprising thing is that the larger members of this family that have been tested aren't actually as interesting as the earlier member of the family, 3003. Every larger member of this family that's been tested has exactly 6 appearances in Pascal's triangle, lining up with 6 dimensions of hypertriangularity that don't include being a regular 2D triangular number. However, 3003 not only has the 6 appearances that are guaranteed from being in that family, but it also is a regular 2D triangular number. It's the 77th triangular number, meaning it's the sum of the first 77 whole numbers, and that, along with the reflection of that, are like a separate magical bonus it has on top of being in that family. So overall, 3003 has 8 appearances. Now, before I get to what else is known about numbers that appear 8 times, let me discuss the general big picture. So far, apart from the missing odd-numbered levels, I've been able to keep ascending in meta-triangularity as I look at larger numbers. So is that something that will continue? Well, one possibility is that that question ends up being equivalent to something called Singmaster's conjecture. He conjectured that perhaps there's some finite amount, that is, some maximum upper limit to the amount of times any number larger than 1 could appear within Pascal's triangle, which also tells us about limits within meta-triangularity that might exist. Like, for example, if this limit was 12, that would mean that numbers larger than 1 could occur up to 12 times, but no more than that. However, Singmaster's conjecture hasn't been proven, and it could also be the case that within the infinite depths of Pascal's triangle, there are places where numbers will repeat more than 1,000,000 times, or more than 1,000,000,000 times, or more than an arbitrarily large amount of times. Despite having so many elegant connections and even simple formulas that describe parts of it, Pascal's triangle and the related concepts like meta-triangularity still contain a lot of mysteries. But Singmaster's infinite family and its surprisingly simple formula weren't discovered until after many hundreds of years into the history of humans studying this array of numbers, so who knows which other simple patterns may just be waiting to be discovered. As far as empirical testing goes, mathematicians have calculated many binomial coefficients that can be used to look for special cases here, and many numbers have been checked, at least the first 10 to the 60th power amount of numbers. Interestingly, if we look at the numbers that appear more than 4 times, they seem to stop happening as much after 24,310. After that, there's a really big gap until the next number that has that trait, which is part of that infinite family, and then the only known numbers that applies to beyond that are the ones in that infinite family that are really spread apart. Even more notably, out of all of the trillions upon trillions of numbers that have been checked, the only number larger than 1 that has been found to have more than 6 appearances is 3003, with its 8 appearances, which I personally think makes 3003 one of the most underrated and mysterious numbers of all time. If we consider 1 to be a trivial case in a way, 3003 could be seen as possibly the most meta-triangular number in existence, and at least the most meta-triangular known number larger than 1 in existence, because if we look for numbers that occur twice, we can look for any whole number larger than 2. And if we want numbers that occur 4 times, we can figure out some number that is non-trivially hypertriangular, such as a 2D triangular number larger than 6. And if we want a number that appears 6 times, we can use that really surprising Fibonacci number formula to generate an infinite family of those. But with numbers that appear more than 6 times, it's unknown whether there's any pattern, and it's even unknown whether any apart from 1 and 3003 exist. Well, at least from what's currently known. Who knows what'll be proven in the future? But for the time being, I think it's fair to consider 3003 as the most non-trivially meta-triangular number. And as far as the most trivially meta-triangular number goes, the way I've been describing things in this episode, that would certainly be the number 1, but I do want to note that there's an alternate way you can view Pascal's triangle, where instead of there being empty space outside it, there's an infinite ocean of zeros zeros on each side. Incorporating these zeros can make some things more confusing, but it does work surprisingly well with many of the mathematical patterns I showed in this video. And if you were to include the zeros, since they would not only appear an infinite amount of times in total, but in fact would appear an infinite amount of times in every row, in that extension, I think it would be fair to call 0 the most trivially meta-triangular number. However, 0 and 1 already get a lot of respect within the world of mathematics, and there are several metrics I could have defined meta-triangularity as that wouldn't have even included them as possible contenders. So really, this episode was more about these very special numbers. Now, for those of you who followed along with my cloverquest in my last episode, I want to provide a quick update about that. I found another 4-leaf clover in my garden, and this time, instead of picking it, I replanted it right here, because this clover plant is more likely than average to grow interesting ones. Anyway, thanks for joining me today to learn about some hypertriangular things. Now, I'm proud to say I created every aspect of this episode myself, all of the graphics, the music. I even filmed all of this one and edited all of it. So I hope you folks enjoyed, and if you do enjoy my videos, make sure you're also subscribed to my bonus Domotro channel in addition to this one. And special thanks to the people who help make my videos possible, such as the people who support in these ways I have listed here. Please consider supporting if you do like my videos a lot. And to all of you, thanks for joining me in combo class today. I'll see you again soon.